Oh, that's someone shows up late.
I got a little bit better.
All right, good morning, everybody. Hope your weekend was good, less exciting than mine. Want to call an audible here or give you a chance to choose your own adventure? What would you do? 2 labs left. One of them is going to be measuring half-life. You don't have the handout for yet. Tomorrow's lab. One or the other. We can either do the interferometry lab that we skipped. It involves lasers and interferometers and all that kind of stuff. Or we can do the spectrometry lab, where we measure the spectral lines for hydrogen, helium, and mercury, I think. Does anybody have a strong preference one way or the other? Spectrometry? Interferometry? Spectrometry? So, okay, so I'm hearing 50-50 here. So this basically comes down to me, which it always did. I just wanted you to feel the illusion of so
Thank you.
here's the thing. I have not given you the spectrometry packet, right? Yeah. So I could give it to you right now and you can read it before tomorrow. You have the interferometer packet, but you probably lost it or something. I will post like a PDF copy of it if we go that way. Spectrometry you've done if you've taken chemistry. We have a more precise instrument that is more finicky to use. So it's a lot harder to get good results out of our physics spectrometers than it is out of the chemistry ones. Whereas the interferometry lab, even though it's kind of coming from the past, right, and it has to do with interference and optics and all that kind of stuff, this is your only chance to do it. You're not going to see that anywhere else unless you go into micrometry. Is that the science of measuring things? Anyway, that's the choice. Let's do the interferometry lab. It is the easier of the 2 labs in terms of the equipment. Like the equipment is, I was going to say, immune to problems. It can have problems, but it's not nearly as big as the spectrometers can have. So let's do interferometry. If you don't have your interferometry lab packet, I'm going to post an announcement saying tomorrow's lab is the interferometry lab, and I'll put the PDF there too, right? But I do need you to read that packet before you come tomorrow. Same thing is true for the spectrometry. You would have to read the packet too, because the equipment's a thing. The thing with the spectrometry lab is that if you don't use the equipment just right, it like fails completely, and you don't know. It takes like 5 to 10 minutes to do a run. And if you've messed it up, you don't know for 10 minutes that it's messed up, right? And then you got to kind of redo it. Anyway, and since you do it in chemistry, I feel justified in not doing it here. So that was a long way around to me just deciding we're going to do the interferometry lab tomorrow. Okay. All right. And then, as we were discussing earlier, your exam 4 will be on 10th. Thank you. 10th of May, which is a Tuesday, 2 weeks from tomorrow. Right? Okay. And I am ahead according to the lecture schedule. We are going deep now. We're going real deep into the heart of atoms. We've spent the last, 3 weeks dealing with electrons and quantum mechanics. Quantum mechanics is the physics of the electron. Now we're going into nuclear physics, the hearts of atoms, the nucleus, and what's going on there. So, first off, some terminology and symbology for doing nuclear physics. We're dealing with all of the nuclei, all of the atoms on the periodic table and their centers, and so we need to know their symbols. But when we write down these atomic nuclei, we have a specific way of doing it. Let's take carbon as an example. Okay, we'll write the symbol, and then we're going to include 2 pieces of information. We're going to include the atomic number, and it's going to be before the symbol but in the basement. And then we're going to put the mass number before the symbol and up on top of the house, so to speak, right? And what we've done here is we've given the rounded value for the mass. So carbon 12. The actual mass on the periodic table right here is 12.0108. So what you do is you write the closest integer value, the rounded integer value of the element. So let's take a look at oxygen. How would we write down oxygen's nuclear symbol? We start with O, right? The symbol. What's the atomic number? 8. And what mass number do we put? You can't read it. The mass on here is 15.9994.
So 16?
You put 16. Okay? So that's how we write the symbols for the nuclei of elements.
Can we get an atomic number of protons?
Number of protons in the nucleus, right? The mass number is the sum of protons plus neutrons. So the nice thing about writing it this way is you can instantly tell how many neutrons that we can instantly tell how many protons there are, but you can also tell how many neutrons there are in this nucleus. How many neutrons are there in carbon 12? You take the 12, you minus 6, and you get 6 neutrons, right? How many neutrons are there in oxygen 16?
8.
8, right? See how that works? Boom, we know the number of neutrons. And knowing the numbers of neutrons becomes important. Protons, the number of protons tells you what the element is. Change the protons, you change the element, you change the symbol. Changing the number of neutrons keeps you the same element, but causes other weirdness in the nuclei, mostly instability. The atomic masses on the periodic table consist of weighted averages. So see how carbon 12 is 12.0108, right? That 0108 represents other isotopes of carbon. What's an isotope? An isotope, same number of protons, different number of neutrons. So technically, carbon 12 is the most abundant naturally occurring isotope of carbon. How do I know that? It's the closest rounded value. In other words, carbon 12 dominates the population of the kinds of carbon that are out there. But there are other kinds of carbon. You've probably heard of carbon 14.
Yeah.
It's used in radiometric dating, which we're going to get to. And carbon 14. You've noticed I've been saying, right, when I say the symbol or anything like that, what's the number tell you? It's the mass number. You're always saying carbon 14, carbon 12, oxygen 16, right? That number that goes on there is indicating the mass number, which is telling you which isotope you're talking about.
And what are the units for mass? It's just
Atomic mass units. We'll get there in a second. Okay? But yeah, it is an atomic mass unit. Again, what's an isotope? Same element, different number of neutrons. And sometimes, especially in nuclear chemistry, they'll say like, there's the element and then it's isotopes. Technically, everything's an isotope. In other words, carbon 12 is an isotope of carbon 14. Carbon 14 is an isotope of carbon 12. They're all carbon. They're just different numbers of neutrons, right? But in general, you don't always have to say carbon 12 if you're just talking about graphite. Right? You just say carbon. It's the most abundant thing, okay? Because carbon 14 is like less than 1/100th of 1% of the other kinds of carbon that exist in nature. It's always you go take a sample of something and you find the weighted averages of the masses of all the atoms that are in there. And then that's the number. And it's internationally decided on by standards bodies all over the place. So when I look at oxygen 16, oxygen 16 is the normal or most abundant stable isotope that exists in nature, but I know that there are other isotopes that are lighter than it. Like I'm guaranteed that there's an oxygen 15 or 14 or something. How do I know that? The actual mass is 15.9994. There's got to be something else that's lighter, that has fewer neutrons, right? But it can't be very much. Or maybe there's a whole bunch of them that are down there. You have to go look in tables to see exactly what the isotopes are. But you can garner some information from it. So Patrick brought up the idea of mass and what the units are. All right. Carbon 12 is 12.0108, okay, on that periodic table right there. And that's in atomic mass units. That's a little lowercase u is the symbol. Sometimes AMU is written down, but most often it's just a little lowercase u is the symbol for atomic mass units. One atomic mass unit is equivalent to 1.660539, and yes, all of those significant digits matter, times 10 to the minus 27 kilograms. How small is an atomic mass unit? Stupid small, right? Like it is just, for this physicist on my own, zero. No, you can't do that, right? We're talking about very small things. You can't just say they're zero. But the differences do matter, and all of these significant digits are going to come into play here in a second. But there's another way to write mass. It's Einstein's way. It's his fault, but he didn't come up with it. An atomic mass unit is also 931.494 mega electron volts per c squared. What's the mega electron volt per c squared? So an energy, right, electron volts per c squared. The rest energy is a mass times c squared. So if you take an energy and divide by c squared, what do you get? You get a mass. And this is what nuclear physics is all about. How does the mass of a nucleon, proton or a neutron, express itself as pure energy or as mass? We're going to trade between them. We're going to try and figure out what's going on, all of that sort of stuff. And so we're going to play fast and loose with this idea that energy can be mass and mass can be energy, and there's a c squared that's along for the ride. But at least we know kind of how to convert between them. And honestly, this one's hardly ever used. Like, by definition, that's true, but nobody calculates anything in kilograms when you're doing nuclear physics. Okay? Unless you're talking about maybe a bulk sample of something, which we should say, like, because we get into molar masses of things, right? So 1 mole of carbon is exactly how many grams? 12.0108 grams, right? So like, if you have the atomic mass expressed in grams, then you know that you have 1 mole of carbon atoms, right? We don't do that very much in nuclear physics. Every once in a while. It's more of a kind of a unit conversion thing. All right. So knowing all this, right, we can go and look up things like the mass of the proton. Okay. According to the text, the mass of a proton is 1.67262 times 10 to the minus 27 kilograms. Or 1.007276 atomic mass units, or 938.27 mega electron volts per c squared. Those are all the same mass being expressed in different units. And you use the unit that is most applicable to the kind of thing, the problem that you're working on or what you're trying to express. The size of a nucleus is on the order of a constant, okay? Your book uses R naught, times A to the 1/3. This R naught is a number. It's 1.2 times 10 to the minus 15 meters. 10 to the minus 15 meters. So that's and the capital A is the symbol for the mass number. Did I get that right? Yeah, okay. Mass number, I'll label it for you. So if you take the cube root of the mass number, multiply by that constant, you get a rough approximate size for the radius of a nucleus of an atom. 10 to the minus 15 is femtometers. Femto, right? We're way beyond pico. So it goes trillionth, and then picometers, and then femtometers, right? This is really, really tiny stuff. Our brains usually can't do anything more than 1,000 before our brains just can't deal with it. All right, let's show you this. So you'll find like this table came out of a textbook long ago. I've always liked how it's formatted. Your book has a table in it very similar to this that gives the masses, right, of all of these things, okay, in all of the different mass units. Notice the carbon-12 nucleus, carbon-12 atom, has a mass that is exactly 12. That's the definition of the atomic mass unit. We say that carbon-12 has an atomic mass of 12 exactly, 0.0000, and then everything else is referenced to that standard. So that's kind of why carbon-12 is a little bit magical. What do nuclei look like? Nothing like this, but if this is what you want to imagine, go ahead. Okay. The neutrons and protons here are the red ones, the neutrons are the gray ones, right? You got neutrons and protons sort of all smushed together in this tight ball. There were a lot of different kinds of nuclear models that were developed over time. Bohr started, after quantum mechanics, they started getting into nuclear physics, and he's like, well, let's treat the nucleus like a liquid drop, like liquid water, and had surface tension on. Well, it turned out that one was totally wrong, but it led them in the right direction. They eventually got to a model that is much like quantum mechanics, where the neutrons and protons are treated like waves and particles, and they have energy levels, and there's a really, really bad version of the Schrodinger equation for nucleons, okay? Like, it gets really bad. We'll kind of skip over that and just pretend that it looks like this. The problem with every nucleus and every nuclear model is this. Coulombs Law, which you haven't had 4B yet, it's okay. It's come up a few times, right, in this force between charged particles. What happens when you get two protons near each other? What do they want to do? Boom, they want to get as far away from each other as possible, right? So, in a nucleus, those two protons are less than 1/100th of a femtometer apart from each other. Coulombs law is a constant times the masses, which in this case are really small, 2 masses of a proton, right? Okay, divided by the distance between them squared. So you're going to put in 10 to the minus 17, 10 to the minus 18 in here. Square it, right? And then divide that into a number that's 10 to the 9 with some 10 to the minus, I don't know what is in here. 19s, 27, I can't, whatever the mass of the proton is, right? So you end up with kind of a tiny number, but it's not 0. In fact, because these two charges are really, charge, darn it. I was just teaching universal gravitation to the 4A students. Charge times charge, right? This is 10 to the minus 16. This totally overwhelms it. Right? You end up with thousands to tens of thousands of newtons of force inside the nucleus of an atom. So what should happen to that nucleus there on the right-hand side? It should fly apart. Every nucleus in the universe should be so fantastically unstable that they should never have been made in the first place. So how do you fix that problem? Because matter obviously is stable.
Make up a new force.
Yeah, you gotta make up a new force. So let's list all of the forces we know so far. Universal law of gravitation, that was in 4A. If you take it 4B, then you've got Coulombs Law, okay, which is the force between charges. So there's 2. So we need a force. We need a force that keeps nuclei together, that's stronger than the electromagnetic repulsion between protons. What should we call it? Strong force, right? Why is it called a strong force? Because it's stronger than the electromagnetic repulsion. So the strong force is the third of the 4 fundamental forces that exist in nature. It acts between nucleons. So the strong force exists between protons and protons, but also between protons and neutrons and neutrons. All you have to be is a particle in the nucleus. So electrons do not feel the strong force. They're not in the nucleus, right? They're out somewhere outside, okay? In their fogginess, right? No part. Okay. It's roughly 100 times stronger when you go measure this strong force. It's 100 times stronger than the electromagnetic repulsion. And since it acts between all nucleons, it's like a glue that keeps the nucleus together and keeps it stable compared to the electromagnetic repulsion from the protons that are in the nucleus. The only thing about nuclei is they come in a lot of different sizes. Carbon-12, that's nice and stable. There's plenty of strong force, and the 6 neutrons and the 6 protons that are in that nucleus are close enough together so that the strong force can act on all the nucleons and everybody's happy. Well, the protons aren't happy, they want to get out, but the strong force is keeping it all together, no problem. But what about uranium? How many protons in the nucleus of uranium? 92. I can't do math. Well, how many protons are there in uranium, or how many neutrons are there in uranium-238? What's 238 minus 92?
146.
146? You guys are amazing. Couldn't do that same way. 146 neutrons? What happens in something like the nucleus of uranium, the nucleons end up getting far enough apart that the neutrons and protons on this side no longer experience any strong force from the neutrons on the other and protons on the other side. They only feel the strong force from their nearest neighbors. Remember, the strong force is exceedingly short range. It only acts on scales of like 10 to the minus 16, 10 to minus 17 meters. And so you can get situations where the nucleus is big enough that the electromagnetic pulsion, which has infinite range, can overcome the strong force's ability to keep the atom, the nucleus together. This is why every single element bigger than lead, that has an atomic number bigger than 82, is naturally unstable and therefore radioactive. An unstable nucleus will give up energy and mass in an effort to become stable, to get to that point where the strong force and the electromagnetic repulsion can balance each other, and so that the nucleus no longer decays. By rule of thumb, anything that is got an atomic number bigger than lead, so starting with bismuth and all the way up, is going to be naturally radioactive, unstable. But you can mess up this stability by putting too many neutrons into the nucleus as well. Carbon-14 is an unstable isotope of carbon. It's unstable because it has 2 extra neutrons, and those 2 extra neutrons are enough to overcome the strong force's ability to keep that nucleus in equilibrium. And so carbon-14 is radioactive and will eventually decay into carbon-12 over a specific amount of time, And if we can figure out those rates, we can figure out how long something has been around. We'll get into that in a bit. This graph is showing you another kind of one of the rules of thumb. As long as you're like, I don't know, atomic number 20 and lower, right? So what's 20 over here? 20 is so like calcium, potassium. I always think of it as like the first 3 rows of the periodic table, right? In the first 3 rows of the periodic table, if your ratio of neutrons to protons is 1 to 1, you're stable. Okay, so take a look at carbon again, right? Carbon 12, 6 protons, 6 neutrons, 1 to 1, stable. But if you go carbon 14, you now have 8 neutrons to 6 protons, right? That 1 to 1 ratio gets thrown off, and so now that's unstable. The dashed line represents the 1 to 1 ratio. The dots represent the stable elements, right? So you can see after the 3rd row of the periodic table, we start to get this deviation, don't we? And elements need to have more neutrons than protons in them in order to be stable. They need more of that nuclear glue that exists with the strong force. Because remember, strong force is both neutrons and protons can experience it. Whereas electromagnetic repulsion is the protons only. So those are some general rules of thumb. Anything on the first 3 rows is generally stable as long as it's not some funky isotope. After lead, it's unstable, and in between is crapshoot. Right? It's just like you gotta kind of have to just look it up and see, is this thing stable? Not that sort of thing. Binding energy. This is a concept that, for whatever reason, seems to flummox a lot of people on the first pass. So make sure I've given you several homework problems for you to cut your teeth on this concept and idea of binding energy. The amount of energy that's required to hold the nucleus together, right, is what the binding energy is. But that's oversimplifying what the binding energy is trying to tell us. There is a lie. Lie is a strong word, and it's not cheating. There is a lack of information that this table presents. Because the mass of the proton and the neutron on this table, right, are what happens when you have a proton and a neutron all by themselves. When a proton or a neutron is part of a nucleus, it actually changes its mass. Let me give you an example. And we'll use this example to calculate the binding energy. In your book, they use some very fancy symbology. They use that symbol for the binding energy, the difference in energy sub BE. Okay? And then they use this. They say the sum of all the MC squareds minus capital MC squared. I don't know why they do this, because this is just overly complicated. Okay? What this is right here is the mass sum of the individual nucleons. What did I just say there? Let's do the example of helium. Okay? Helium, regular everyday stable helium. Okay, what would its nuclear symbol be? The atomic number is 2, and what's its mass? 4. All right. So 2, 4, how many neutrons? 2. 2 protons, 2 neutrons, right? So helium consists of 2 protons plus 2 neutrons. And we are going to calculate the total mass of the helium nucleus based on that table that I just showed you, right? The mass of a proton and a neutron sort of all by themselves. We are doing Legos, right? And we know the masses of the individual Legos. And so if you know that each piece of your Lego set is 1 gram and you use 10 pieces, then what should the mass of your Lego be when you got all 10 pieces together? 10 grams. That is not what happens in nuclear physics. The Legos change their mass depending on how many of them there are in the structure. This right here is I'm not responsible for this. The mass, okay, of the nucleus in nature. So, all nuclei weigh less than they should if we took the masses of protons and neutrons and simply added it all together. Let's do the example of helium. Okay, so for helium, the mass of helium, if you go just measure the mass of a helium nucleus, is 4.001506 atomic mass units. And yes, all of those digits matter. This is not normal for physicists. Physicists were like, nah, that's 4, right? Can't do that. Nuclear physics, all the significant digits they give you are very important, okay? The mass of a proton, all by itself, is 1.008665 atomic mass units, and the mass of a neutron is 1.007276 atomic mass units. Okay? So, when we go and we put together, right, we say we take our 2 protons plus our 2 neutrons, right? So we 2 times 1.008665 plus 2 times 1.007277. We just took 2 neutron Lego pieces and 2 proton Lego pieces and we put them together, right? And we get the total mass. Yes?
I think you have the mass of the proton and neutron backwards.
I probably do. It wouldn't be the first time. Because they're numbers, and I just told you they matter, but that doesn't mean they stick in my head. Proton is the lighter one, right? So, easily fixed. In my notes, but maybe not yours. Thank you. Neutron. Okay. And when I do that, 882. There's the total from my calculator, which is immediately suspect because it's me and involved. I'm pretty sure that one's right. Note that the value we got, adding them together, is bigger than the value that exists in nature, right? To find the binding energy, I take the value I got playing with my atomic Legos, and I subtract off the value that it actually is when you go measure it, and we get a difference of 0.030376 atomic mass units. That mass is a missing mass. And it tells me that the protons and the neutrons in the nucleus of helium are lighter than they are when they are by themselves. In other words, when I put the Legos together, the Legos changed their masses because they were together. Why? Where did the mass go? E equals mc squared. So where did the mass go? It got turned into energy. What energy? The energy of the strong force that keeps the nucleus together. The nucleons gave up some of their mass so that they could be bound together by the strong force. That's where the strong force gets its energy from. That's a lie, but it's a good enough lie. So this binding energy, it's weird, isn't it? I'm expressing it as a mass unit, right? So how is this an energy? Well, we can convert this into a mega electron volt per c squared value, right? we have a conversion factor. One atomic mass unit was, what was it? 900 and, I didn't write it down. I did, I wrote it down on this paper. 931. 494 mega electron volts per c squared. So I use that conversion factor and I find that this value is 28.295 mega electron volts per c squared, right? And since E equals mc squared, the rest energy, right? I can take my 28.295, the mass, mega electron volts per c squared, and multiply by c squared. And I get 28.295 mega electron volts as the binding energy. This is why in nuclear physics, a nuclear physicist will often say the energy is 0.0303 atomic mass units. And you go, what? That's a mass, not an energy. And the nuclear physicist will look at you and go, well, they're the same thing. You're just arguing about a c squared. So fine, if you don't want an atomic mass units, it's 28.295 mega electron volts. Is that better? Right? No, not really. Okay? For a nuclear physicist, energy, mass, mass, and energy, you can distinguish between them, but it doesn't matter. They're the same. That's where binding energy comes from. And try to make it that simple, right? Take the mass of a proton, mass of a neutron all by itself, put your, use the mass number and the atomic number to tell you how many to put together, find that number, then subtract off the given value for what that nucleus's mass actually is. Whatever that difference is, that's your binding energy. Right? Then, I think the reason it gets a little bit screwy in people's minds is then there's graphs like this. I actually love this graph for a lot of different reasons. But what this is a plot, okay, of mass number. So as this gets bigger, we're going up the periodic table, right? Compared to the binding energy per nucleon. So here we formed a ratio between the binding energy, like we calculate the binding energy in helium. How many nucleons are there in helium total? How many protons and neutrons together? 4. It's the mass number, right? Number of nucleons, protons and neutrons is 4 in helium. So you take the binding energy, whatever, 28, whatever, divide by 4. And you've got this number, this ratio, right? And then you can do that for every element, because every element has its own binding energy, right? Its own number of nucleons. And you get this curve, and this curve is really cool. The binding energy per nucleon for hydrogen is stupid small, right? And then it goes up and up and up, right? There's heliums up there and some others in there. And do you see how it kind of peaks right there at iron 56 and nickel 62? Those are the elements with the highest binding energy per nucleon, meaning that they contain the lightest versions of the protons and neutrons in the universe. More binding energy more mass of those things has been giving up to the binding energy, which is why iron and nickel, iron, cobalt, nickel, are the most stable elements in the universe. We won't have time to get into this semester. We need a Physics 4D class for this. But in stellar fusion, stars combine hydrogen and hydrogen into helium. And then helium and helium into carbon. And then carbon and carbon fuse into everything else up to iron. When a star that has sufficient mass runs out of its carbon-carbon fuel, it cannot fuse anything else together. It has to stop at iron because iron is the most stable element and you can't fuse iron together with iron to get anything else. And then that star will supernova and explode because it's run out of fuel to balance the gravitational attraction, all that kind of stuff, and it'll either turn into a neutron star, pulsar, or a black hole. Okay? And so that kind of begs the question, if iron and nickel are the most stable elements in the universe and you can't make anything past iron in stars, energetic things in the universe. How do you get the rest? Where does gold come from? The answer is, it comes from exploding stars. Everything past iron on the periodic table once was created in the heart of a dying star, as it erupted in a supernova, an event that I can't even possibly begin to express to you the kinds of energies that are involved there. You need 350 million Kelvin before you can fuse carbon and carbon together, right? And then you need a supermassive explosion to be able to make everything else. It's not fusion, it's a thing called neutron capture and a bunch of stuff that goes on. But the point is, anything past iron and nickel, that was made in a supernova. Gold, silver, platinum, uranium. Uranium we dig out of the ground, where did it come from? It was a supernova. Long before this Earth was ever made. And then gravity gathered it all together, and then we go dig it out of the ground and put it in bombs.
So cool.
It's kind of an irony there, isn't it? Gold. Why is gold so precious? It's shiny. Right? It's shiny, and there's not a lot of it, and it's bleak, right, or whatever. Where did all the gold come from that is in planet Earth? When I proposed to my wife, I told her that I could think of nothing better than to honor our love and commitment to each other than to give her a supernova remnant to wear on her finger. She said yes. Why? Yeah. Why, Mr. Balogh? Yeah. Every once in a while, every several years, I'll forget my lunch or something, and Mrs. Balogh will bring it down to me, and she'll come into the classroom, and I'll stop the entire class, and I'll tell the class, right? You have 3 minutes to ask Mrs. Balogh any question you want. Any question, I will not say a thing, and she will answer truthfully. We've done this game before. And then, so questions have varied over the years. My favorite was, she had come in, given me the lunch. I'd given her an Oklahoma Hello, which if you don't know musicals, you don't know what that is. I give her the bending kiss, right? Down like this, give her a big old smack on the lips. It embarrasses her, it turns her bright red, it's so full of love. And so I do that, and then I say, okay, you can ask her any question you want. I kid you not, I had not finished my sentence before one of my students threw his hand in the air and said, does he yell like that at home? She's like, no. Don't call CPS. All right, so that's binding energy and binding energy per nucleon. Radioactivity. When the nucleus is unstable, it will work tirelessly to become stable. It really has no other choice, okay? The strong force can't keep it together. Electromagnetic repulsion is taking over. And we already talked about Marie Curie, right? And all of her work with her husband Pierre in isolating and discovering the 3 principal kinds of radioactivity. They isolated radium and then some other radioactive isotopes that were contained in that pitch blend that Henri Becquerel had handed to them. They got sick. Now, Pierre would die tragically in a street accident. He would be run over by a horse and carriage on his way home one evening, carrying flowers for their anniversary. Yeah, it was pretty bad. Eyewitness accounts suggest that he just wasn't paying attention. He was thinking about something and just stepped into the street right in front of the carriage, between the horses and the carriage. And got run over. Marie would go on after that. She would found a women's college. She would have a scandalous affair with another scientist in the Paris community. Don't get the idea that these scientists are, upstanding examples of moral behavior. But that doesn't detract from the work that she did with her husband, and then later the work that she did by herself. She went on, continued on their research. She won 2 Nobel Prizes. Did I tell you this? She won the Nobel Prize in Physics with Becquerel and her husband, and then later won the Nobel Prize in Chemistry. First person to win 2 Nobel Prizes, first woman to get a Nobel Prize. Only woman to get 2. But anyway, their lab, so they were isolating and purifying this radium in this sample, and to do that, they had to concentrate it down. They had to get rid of the other elements and just get this one out. And they had a lot of chemical processes they went through. What they didn't know at the time, right, is they took tons of pitch blend and brought it down to these really tiny samples of radium, is that they were increasing their radioactive exposure, right? That more and more of this radioactive element was being concentrated in smaller and smaller space. And to this day, you can't see her original lab books without being exposed to too much radiation. You can go visit where they're kept, but they're kept in like a lead-lined box. And you're limited to like 5 to 10 minutes at a time of being able to read the pages, because the pages are so radioactive. The doorknobs in their labs are still radioactive, right? The amount of radiation that just the lab and them. They would describe how they had sores on their hands, they had funny cuts and lesions on their hands, and they couldn't understand where it was coming from. It was coming from the radioactivity that they were discovering, the act of discovering. Marie would die of natural causes, probably not cancer, like amazingly, right? There was nothing in the scientific acumen at the time for them to connect sort of radiation damage to life expectancy. It's possible, but again, the medical record is not detailed enough to be able to really, other than she died of natural causes at old age. The 3 kinds of radioactivity that they discovered, they creatively named alpha, beta, and gamma. I wonder where they got that from. And they had, all 3 of these had different properties. Right? Alpha particles would bend one way in a magnetic field. Beta particles would bend the opposite way with bigger curve. And then the gamma rays would go straight through the magnetic field like it wasn't even there. And so this instantly told them something about these 3 different kinds of radioactivity. They knew right off the bat that alpha and beta were oppositely charged, because they were bending different directions in a magnetic field. Again, in 4B, we learned how charges get influenced by magnetic fields. Bottom line is, positives go one way, negatives go the other. If you know the direction of your magnetic fields, you know if you've got a positive or negative charge. So they knew instantly. The fact that the beta particle turned faster, had a shorter radius of turn, told them it had a smaller mass. So they could go measure the mass of the different particles. They found out that the mass of the alpha particle matched the mass of a helium nucleus. And so that's what the alpha particle is. It's the nucleus of a helium atom. The beta particle turned out to match the mass of an electron. And so a beta particle is an electron. The gamma ray, not being influenced by the magnetic field at all, had no charge and turned out also to not have any mass. What's the only thing that doesn't have mass? Light. So it was a gamma ray photon. So energy in all of its forms, mass and light, right, coming out of the nucleus in an effort to become stable. In alpha decay, and they are kind of listed in order of their increasing oogie booginess. Whenever I talk about radioactivity, I'm sure that what people get in their brains is pictures of like 3-eyed fish, zombies, or like, the Fallout games or something, right? It's always sort of this post-apocalyptic thing. We're going to talk Wednesday and probably in the next week radiation is everywhere, it's all around you, and it's natural. Like, our biological systems can't function without it. In fact, when we are cut off from radiation, our cells go haywire, right? Not cancer haywire, but they just stop functioning the way that they should. So we'll get into that. The thing about alpha, beta, gamma is that helium nucleus can be slowed down by a piece of paper. It can be stopped by about a meter of interaction with air molecules. It will come out of the nucleus, interact with other things around it. As soon as that helium nucleus slows down and picks up 2 electrons, what is it? It's helium. And you put it in balloons and give it to clowns and birthdays and stuff, right? The beta particle, electrons, they aren't so bad, right? Give them enough kinetic energy, right? And they can become ionized. All 3 of these are ionizing radiation, but it's the gamma that you really have to look out for. And this is sort of a lie too, but we could do, there's a quiz question that sometimes I ask, we won't do it as a quiz. If I baked you 3 radioactive cookies, I baked you an alpha cookie, beta cookie, and a gamma cookie, and I gave you all 3 of them, and I said you have 3 choices. You must eat one of the cookies. One of the cookies you can put in your pocket, and another cookie you can hold in your hand. What would you do to minimize your exposure to radiation? Which one would you hold in your hand? Alpha. Why would you hold the alpha cookie in your hand? It can be stopped by a piece of paper or your skin. Your skin's thicker than paper. Okay? So, holding an alpha cookie in your hand will not give you any radioactive exposure inside you. And maybe a little bit on the surface of your skin, but skin is dead. It sloughs off. It's fine. Okay? Skin's alive. I know. Top layer, it sloughs off. The beta cookie. Where do you put the beta cookie? In your pocket. Why do you put it in your pocket? Aluminum, clothing, couple layers of clothing, perfectly fine for stopping a beta particle. In fact, wearing a lab coat with a shirt underneath it and an undergarment, you're fine. Okay, beta's not going to come anywhere near you. Okay, so that leaves the gamma cookie and the only choice. Why do you eat the gamma cookie? Inside or out, it's going to get you. It doesn't matter. Okay, you need like 6 inches of lead to stop a gamma particle, right? They're coming for you. Okay. I hope I have time for this. The different decay processes, the alpha, beta, and gamma decay processes are important. They tell you what's going on in the atom. So for example, in alpha decay, the pattern, okay, is to take the parent, okay, with its atomic number Z and its mass number A, and you are kicking out the helium nucleus, right? The helium nucleus has an atomic number of 2 and a mass number of 4. That leaves behind a child particle that is, well, we've got to balance things here. Kind of like a chemical equation, you got to balance it. So the child particle is going to have an atomic number that is, how much smaller? 2 smaller, and an atomic number that is 4 smaller. That's the pattern, right? So here we have radium-226. It undergoes an alpha decay. Why does it become radon-86? It loses 2 protons, and when you change the number of protons, you change the element. We go from radium, right here, number 88, we lose 2 protons, so we become radon, hey, noble gas, right? In this case, 222. It's 222 because we started with radium-226, we subtract 4, we get 222. So you know exactly where you're going to end up in this alpha decay. Why is this one important? Radium naturally occurring element, the element that the Curies, right, isolated and discovered, naturally decays into radon, a noble gas. One of the features of noble gases is that they don't like anybody, they won't react with anything, and so it just sticks around. Radon also is the heaviest of the noble gases. So if you dig in the ground and you make a hole in the ground, and the ground has radon in it, and that radon is decaying into, it's got radium in it, and it's decaying into radon, where does your radon end up? Bottom of your hole. A hole in a house is called a basement. Basements have this feature that they are always where? Underground, right? They're dug into the ground. I know here in Fresno we don't have very many of them, so nobody knows what I'm talking about. In the Midwest, there have basements everywhere. Why? Because it's easier to dig in the ground. There's tornadoes. So basements in the Midwest have radon in them. Radon is a noble gas, doesn't react with anything, so it sticks around. You go down to play video games in your basement or live in your parents' basement, and what are you going to be breathing in all the time? Radon. You now have an alpha emitter in your bloodstream. Is your skin going to protect you? Are leukemia rates higher in the Midwest than they are on the West Coast? That's why there's government numbers. 1-800, oh my gosh, I have radon, or whatever the number is, I can't remember what it is, right? You can call the feds, and they will send you radon test kits. And you can open these things out, you collect for a week, you send it off, they tell you how much radon is in there. There's little detectors, so we have fire detectors here, right? We also have the earthquake detectors that tell our phones when the earthquake's coming, right? In the Midwest, they have radon detectors, and just stick them in their basements, and when that radon detector goes off, bend over, kiss your rear end goodbye. No, I don't know what happens, because I grew up in California. But they're very conscious of radon in the Midwest. We have no idea what it is, right? Another source of alpha decay, this is the interior of a smoke detector. If you open up a smoke detector, you will see that there's some, I can never say it, americium-241 in it. And that's a radioactive isotope. It's a man-made radioactive isotope. And that radioactive material is producing a beam of alpha particles. Remember, alpha particles get foiled by air molecules and especially smoke particles. So as long as there's no smoke in the detector, the stream of alpha particles is nice and strong. The detector says there's no fire. As soon as the alpha particle stream goes away, because in theory, there's too much smoke in the air, too much particulate, the voltage drops and the detector goes off. It says, wake up, get out of the house.
Is that how even the newer ones work too?
Yep. Yep. You're not supposed to throw away these, you're supposed to recycle them because they can get the radioactive isotope out. So that's your closest source of man-made radioactivity is the smoke detector in your house. This is beta decay. Trying to decide if I'm going to have time to do what I want to do. When does this class end?
10:50, right?
10:50? I think we do. You know what? I'm going to come back to beta and gamma next time. Okay? We'll skip over beta and gamma. It's not that you can't figure them out. It's just fine. There's just some weirdness going on. What the heck is an electron doing coming out of the nucleus? We've got to answer that question. Okay? But what I want to do instead is a demonstration of this. And I think I've got just enough time, about 20 minutes, to do this, okay? So to do this demonstration, what I need you to do is I need you, how many people are here? There's about 40 of us here. Everybody take 3 dice. Does that make sense? You need 3 of these, right? Start sending these back. 6, 1, 2. We'll go that way. That one. And then we'll do over here. You guys send it this way. Have it come back over this way. Okay. Everybody needs 3, and then you need 3 pieces of paper. So you need 3 die, 3 pieces of paper. Do not keep the die and try not to drop them. While you're getting all that sorted, we need to talk about Half-Life and what it is. Half-Life is the greatest video game series that has ever existed, bar none. Right? Its main protagonist, its hero, is a physicist with a PhD from MIT. His name's Gordon Freeman. He never says a word. Carries a crowbar. The aliens get messed up. Okay? Oh, there you go. We'll pick those up. We'll pick them up later. Don't worry about it. We have a big pickup to do here in just a bit, so hold on. Half-life is a measure of how long it takes for a nucleus to decay. We've been talking about how nuclei are unstable and they want to get to a stable point. Half-life is a statistical measure of how long it takes a nucleus to decay. In truth, a single nucleus will decay based on the universe's random number generator. There's no way to predict when a single nucleus is going to do anything. But when you take a population of nuclei, a mole's worth of carbon-14, that's, Avogadro's number of nuclei, you can start to pull out patterns in the statistics. And so what I've handed out to you today is a model for half-life. Each of you represents not 1, not 2, but 3 unstable nuclei. That's what your dice are. Okay? And what is the probability in rolling one of those die that it will turn up the number 1? It's 1 in 6. There's a 1 in 6 chance when you roll a die that you're going to get the number that you were looking for. So we're going to model a population of radioactive material. By the power vested in me by the state of California and the fact that I control all of your grades, I now make you a radioactive material. You will be called Balogh. Okay? Each of you represents 3 of those radioactive nuclei of polonium. The reason you have 3 is because we need at least 100 for this to kind of work out really, really well. But what we're going to do is we're going to plot, okay, time versus number remaining, number of nuclei remaining, okay? And we're going to go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 30. I said there was 40 of us in here. And I each gave you 3, right? So that's 120, isn't it? 60, 70, 80, 90, 100, 110, 120. All right. So we're starting at time 0 with 120 unstable nuclei. We're going to simulate polonium and we're going to simulate its decay process, and we are going to try to tease the concept of half-life out of this process, this simulation. For every time step that I'm going to give you, what I'm going to do is I'm going to say, roll your die. Okay? What you're going to do is you're going to pick up all of your die. Don't do it yet. And you're going to roll them. Try not to get them onto the floor. Roll them on your table, right? And then, for every number 1 that you see, you're going to do 2 things. You're going to take that die that's rolled 1, and you're going to set it aside, and you're never going to roll it again. It has decayed, right? But when a nucleus decays, it emits a radioactive particle. Take one of the 3 pieces of paper that you have, crunch it into a ball, and chuck that piece of paper to the front of the room. Right? You are emitting, right, the radioactive particle. I will be the Geiger counter, and I'm going to count the number of radioactive decays that happen in that time step, right? Does that make sense? So, On the next time step, let's say 2 of your dice have 1s on it. You've removed those, right? In your next step, how many are you rolling? 1. You get the idea? You might have to roll 6 or 7 times before any of them turn into 1, so you'll be rolling 3 die, right? But you're going to only roll them when I tell you, because we got to keep everybody at the same time interval, okay? And when it comes to throwing those pieces of paper to the front of the room, there are rules. Rule number 1. Hit me and you get an F. Rule number 2, if you're in the first 3 rows, duck.
Okay.
Rule number 3, if you have more than 1 decay in a time step, like 2 or 3 of your dice all come up 1s, okay? Please throw those pieces of paper separately. Not all 3 at the same time, 2 at the same time, okay? Do 1 and then do the other. And please, if you can remember rule number 4, 3.5, if somebody next to you is throwing, try not to throw at the same time. Because I'm trying, like I have to count these, right? And I need to get an accurate count of what's coming. Does that make sense? Okay, so let's start. Time number interval 1, right? Okay, you're gonna shake up your die and go ahead and roll them. And then based on the number 1s you have, throw pieces of paper.
Oh, you will read it.
Okay, I'm gonna count 15. If one of them doesn't make it, don't pick it up and throw it again. I've counted it. Okay, as soon as I see anything in the air, I count it, right? So I counted 15 there. So what's 120 minus 15? 105, somewhere right in there, right? Okay, so we'll write 105 right there. Okay, so again, those of you that threw a piece of paper, you're rolling fewer die, right? Okay, so roll again. Right? Already counted that one. All right, so that was 12 that time. Kind of to be expected, right? There was fewer total. Right? And so, all right, that's fine. So what's 105 minus 12? 93-ish. Oh, come here. Oh, don't roll yet. So there's 93. All right. Do it again. Oh, interesting. Okay, there were 13 that time. Even though there was less to begin with? 93 minus 13 is 80, right? Somewhere in there. Okay. Roll again. All right, 20 that time. What happened? There was a lot more that time, even though there was fewer to start with. What's the point here? It's random, right? The probability of decay at any one given instant in time is totally random. How many of you have no die left? Okay. How many of you have 3 left? How many of you have 1 left? A lot of you only have 1 left, right? How many have 2 left? We're all over the place here, aren't we? Right? We got people who have already gone out, and we got people that still have 3 left, right? Roll again. That was it?
I only counted 3.
3. many?
4.
4? So 56?
Yeah.
Okay, again?
You know that one? I don't have babies.
5?
I should go to the
All right, we're gonna speed things up here just a little bit. Okay, get down to 49 here, right? Okay, you can see the trend, can't you?
Yeah.
Okay, so I can have you keep rolling. It would take a while for us to get there, but let's just kind of fit the curve here. I did that kind of sloppily. Okay, but that curve would look a little bit like this. The half-life is the time it takes for the sample to decay, for half of the nuclei to decay. Half of 120 is 60. And that looks like it's 4.1 Balogh time units. The half-life of polonium is 4.1 Baloghs. That's how you do it. We did a fit based on a statistical measure, right, of a random set of events that gave us a singular value for how long it takes. All right, we have just barely enough time to repeat this. I need you to come up here and pick up, you need 3 pieces of paper, right? So get up here, pick up paper, and get some more paper if you've lost some, right? Make sure you end up with 3 pieces of paper again.
You're even aiming for it. It's all about how much.
You've got pieces of paper out here if you need to make more.
I'm not just taking.
All right. This time we're going to change the nature of polonium. Okay? We're going to go to an isotope of polonium, polonium-3. Polonium-3 will decay if a 1, 2, or 3 shows up. So what's the probability of decay now? Half, right? So we expect there to be more decays per time, right? Concentrate on the radioactivity, the amount of events per time, and the half-life of Balogh polonium-3. Okay? So, go ahead and roll and throw. All right, there's about 40 there. Okay, I lost track. One of the first times I started doing this thing was right after Al Gore lost the election and somebody demanded a recount. So right about there. Okay, we'll call for it. All right, do it again. So, how radioactive is polonium-3 compared to polonium? Higher, isn't it? For every time period that goes by, there's way more particles coming out of it. Okay, do it again. There wasn't very many there, right? Okay. So maybe it's shallowing out a bit. Okay, go again. How many people are like out of dye? Yeah, should be a lot of you, right? Does anybody have 3 left? No, okay, every once in a while that happens, right? But you can see we're getting a lot fewer now, right? Which means that this thing is really tanked. So the curve looks more like this, doesn't it? Okay, if we go to look at the half-life, we're at like 1.3 Balogh time units. The more radioactive a substance, the longer or shorter its half-life. It's shorter its half-life, which goes counter to the way most people think of radioactivity. They tend to associate things with long half-lives, like uranium. Uranium-235, 238 has a half-life of 4.5 billion, with a B, years. And yet people think uranium is super radioactive compared to iodine 52, 51, I can't remember exactly what the isotope is, which is what is used in radioactive tracers that are injected into people for medical diagnostic routines. The half-life of iodine, I think it's 52, is measured in minutes. Which of those two is more radioactive? Iodine, by a long shot. Why is it okay to inject iodine into a person but not uranium?
The half-life?
Because
The amount of energy that is absorbed does not depend on the half-life. There's a lot more activity for a much shorter period of time. The iodine, within a matter of 60 minutes, is completely stabilized, and the person's no longer being affected by any radiation. You take a chunk of uranium and put it in your living room, you have 4.5 billion years before half of it is gone. Right? So a lot more exposure to radiation from uranium than from iodine. Come up, get 3 pieces of paper, put them in the recycling bin. Give me my dye back to the containers here. Bring the yellow containers up here, we'll fill them up. So there should be 6 yellow containers. The janitors love me. And I will see you guys tomorrow for the interferometry lab.